I'm going to talk today, are we recording? I'm going to talk today about confidence intervals, if I can get in enough, if I can fit this in, intervals, hopefully. I'm also going to talk about proportions of successors of Bernoulli trials. I'm going to talk about estimation of proportion. I think that's quite a lot to discuss. I'm going to link all this to Bayes' theorem. Bayes' theorem, plus a new concept, which is likelihood. It's quite a lot to get through, quite a lot of rather gnarly statistics here, quite a lot of theory here. Let's just have a look at Bayes' theorem. I'll just write it out again. I might not get up to confidence. I wrote that first because that's what I want to get up to, but I might not have time for that. Let's just write Bayes' theorem again. The probability of H, let's say J given D, equals P of HJ, which is your prior, P of D given HJ. Let me change colours just to make this a little bit clearer. So this one here is your prior. This one here is your likelihood. Likelihood. And we divide by a normalizing factor. Sigma over I, P of HI, P of D given HI. So there's the denominator. And the denominator here ensures that the posterior probs sum to 1. So if we take all the hypotheses that are available to us and add up the posterior probabilities, the sum of the numerators will be the denominator, and therefore the probabilities all add up to 1. This, of course, is your posterior probabilities. And I've been talking about Bayes' theorem in many, many ways, but this is the canonical use of it. It's not quite an Achilles heel of Bayes' theorem, but implicit in all this is the assumption that exactly 1 of H1, H1, H2, ... up to Hn is true. So my hypotheses, we've done lots and lots of examples. These were the different fathers that we might have considered for the paternity case that we looked at. This could be whether I was right or Annabelle was right about the umbrellas and so forth. It's not an Achilles heel, but it's an assumption that's built into the mathematics that exactly one of these hypotheses is true. We don't know. We've got opinions about it. We've got some data. Bayes' theorem links those two things together, those two features together. But we start by knowing that one of them is true and only one of them is true and we don't know. They've got to be, the word you use in mathematics is exclusive and exhaustive. Quite tightly packed nomenclature. Exclusive means that if that's true, then none of the others can be true. You can't have both of them being true. They don't overlap at all. And exhaustive means that we've exhausted all the possibilities. There can't be other hypotheses that that might be true that we haven't considered. We've got to put them all in there. I guess if you wanted to be sure, then you could call the last one everything else combined. I say again that Bayes' theorem is, well, the theorem itself isn't controversial, but the use it's put to in contemporary statistics is certainly very, very, very controversial, causing fights among statisticians and conflict in the discipline which has not been resolved. So now I'm going to consider a set of Bernoulli trials with probability P of success. I'm going to consider 10 trials of which 3 were successful. So you toss the coin 10 times and you have 3 successes. Oh, thank you very much. It was a loose plug and we typed it in and we're sweet. So thank you very much, and I'm sorry to disturb you. Thank you very much. I want to hammer the point home again and again and again and again. In my world, I take 10 photographs of my kids and I've got 3 of them where I've got all 3 standing still so I can take them. In my world, I've got 10 mortgage payments and I can meet 3 of them without a letter from the bank telling me I've gone overdrawn. In my world, I've got 10 pairs of shoes and I've got 3 of them with no holes in the bottom of them. This is the world I live in. You have to think right now what your 10 trials are from your world. It's your fish, I suppose, and your machine, is it? Yeah? You all got to think, when do I do 10 trials? Or I might go shopping 10 times, and on 3 of them, I don't lose my little boy, and he's going to run off, and I have to go and find security. Whatever it is. You have to think of your example. What's yours? Yours is your game, isn't it, with your wife, with the quiz show. Yeah? So you get 10 trials, and 3 of them, you score higher points than your wife, yeah? Whatever it is that's coming from your project or from your lives, don't restrict yourself to your project, but your portfolio is a good place to start. What your trials are, you think of that. And I want to know what P is. Well, it's 3 out of 10, isn't it? 0.3. I'm probably not telling you anything you don't know here. Most people will just say it's 0.3 and stop there. But P equals 0.29999 is okay. And I'm going to put okay in scare quotes because at the moment, okay just means, yeah, it sounds about right. It's got truthiness. P equals 0.30001 is okay, again in scare quotes. I'm putting the scare quotes on because I'm going to give you proper mathematical definitions for what okay means. And I'm not using any word I'm not using any loaded vocabulary. I'm not using any vocabulary that's got statistical meaning. I'm just saying okay. What about P equals 0.35? Yeah? What about P equals 0.999? Let's just think about that for a minute. If P really was 99.9%, yeah, 99.9%, you don't see this very often. If P really was 99%, you're going to get 10 out of 10 most trials, yeah? So that's not okay in some sense, which I'll make precise later. What about P equals 0.0000001? Is that 1 in a million? It's 1 in 100 million, that. If that was your probability of success, and you got 3 out of 10, what would you do? Something's wrong here. So that's no. What about, anyway, you seeing what I'm doing? At the very extremes, you've got some no's, and right in the middle, you've got some probably all right.
And 0.35 maybe all right?
0.3, well, we'll see this. We'll see this. What about 0.5? What about 0.5? If I gave you a real, actual coin and said, let's toss it 10 times, what does it come up with? And it came out heads 3 times. You wouldn't say to yourself, I don't think that's a 0.5. You'd say,
let's do it again.
Let's do it again. 3 out of 10 looks all right.
Could be 7 next time.
Could be 7. Okay. So what I'm going to do is this. I'm going to introduce a new concept. I'm going to talk about a prior probability density function. You'll recall that a probability density function is something like this. This is a PDF. This is a Gaussian one. Probability density function, and we can work out areas for probabilities of it being between 2 values and so forth. And it never goes negative, and it's a nice function. I'm being a little bit coy about the precise definition of PDF because to give you a proper definition of PDF, you need a lot of mathematical machinery that's not helpful in this context. This is no good for a probability because the Gaussian PDF is infinitely wide. Infinitely wide. And we know, in fact, that 0 is less than or equal to p is less than or equal to 1. So however narrow you make this Gaussian, it's still going to stick its nose out of 0 and 1. So the Gaussian PDF is no good. We need an alternative. We need an alternative to Gaussian. And what I'm going to do is I'm just going to give you this. I'm just going to give you this distribution. And I'm just going to see how it develops. Okay? It's a matter of some concern to me that in my research that this is a very, very, very common problem. Estimating the probability of success of something from limited data is a very common problem. I will expect all of you to do this or something like it in your portfolios. So what we do instead of the Gaussian is to use a thing called the beta distribution. As a prior. And it looks like this. I'll draw it in a second. I just want to remind you before I draw it that when we were fooling around with a Gaussian, we could slide it left and right by the mean, and we could make it sharper or more diffuse by changing the standard deviation. We've got those two nice degrees of freedom, those 2 nice parameters there, the mean moving it left and right, standard deviation making it more spiky or more flat. You don't have that freedom in the 0-1 world. You can't just move it left and right. It's a little bit more complicated, a little bit more confusing. I'll just draw an example. This is an example, and then I'll give you the mathematics. Okay? You want something that pinches off to 0 here, pinches off to 0 here, and it's got a nice, smooth mathematical shape. And the PDF is this. I'm going to have to introduce this slowly. It's something which I'm going to call some constant spelt with a K, just to remind myself that I haven't defined it yet, times this, p to the power alpha minus 1, 1 minus p to the beta minus 1, where alpha and beta are parameters to be chosen. They are like the mean and the standard deviation of the Gaussian. They're not mean and standard deviation, but they play the same role in this distribution as mean and standard deviation or mean and variance play in the Gaussian distribution. The constant, which I've just casually written down as constant, the constant is chosen. The constant is defined so that the area equals 1. You see, I can scale this distribution up and down, but I need the area to be 1 because I know my p is between 0 and 1. I know it's somewhere in there. It might be very small, it might be very big, it might be, I don't know where it is, but the area equals 1. In fact, I'm going to write it in. Area equals 1 because I know my p's in there somewhere. CF, Gaussian, actually, I'll change colours. This bit, oh, for goodness sake. This one here, this is your constant. There's no x in it, you see? X only enters here. So I've got my distribution. There's the mean. There's the standard deviation, so the standard deviation squared. So this constant here is ensuring that the area equals 1. You remember this from when I was talking about the Gaussian distribution? This bit does the work. This bit makes the area equal 1. So what is that constant? Funnily enough, a couple of weeks ago, somebody asked me what this constant was, and I couldn't remember what it was. And instead of looking it up, I tried to derive it. It is a very, very difficult calculation. Was it? I can't remember who did it. It was either Legendre or Laplace. It was one of that bunch. There is absolutely no way any human being can do this. It just beggars belief how clever the derivation. It needs calculus, but calculus to the power calculus, unbelievably difficult. So I'm just going to give it you. I'm just going to give you a notation here. N question mark. What's that? It's not a question mark, is it? Shout, but exclamation mark. Factorial equals n factorial, yeah? Write it out a bit more neatly. Equals n minus 1 factorial equals the gamma function, gamma of n, or the gamma function. This symbol here is a Greek letter gamma, which I think is a g sound, but I'm not an expert. It's a gamma. Gamma. Oh, yeah, gamma function. So it's just a nice piece of notation. Invented by Euler in the 18th century. They had the factorial function way, way, way before that. That's been known for thousands of years. He put this minus 1 in here. Normally when you've got a function, what Euler wanted to do was to define 1.5 factorial or 1.2 factorial, because you've got 1 factorial, 2 factorial, 3 factorial on the integers, and Euler wanted a factorial function that would work for any value, for 1.5 or 1.6 or 10.2. So what's 10.2 factorial? It's the kind of thing mathematicians ask. But instead of that, he put this minus 1 in there. And on a Monday, Tuesday, and Wednesday, I think that was the greatest stroke of genius he's ever had. And on a Thursday, Friday, and Saturday, I think I'm going to find his grave, I'm going to dig his body up, and I'm going to abuse it. Because that minus 1 is the most stupid piece of mathematical idiocy I've ever seen in my entire life. And on Sundays, I don't know. Sunday's rest. So we've got this minus 1 factorial. So for example, gamma of 4 will equal 3 factorial equals 6. Gamma of 0, sorry, and gamma of 1 equals 0 factorial equals 1. Gamma of 0, undefined. It's a wonderful function. It's a wonderful function, but this minus 1 alternately delights and disgusts me. Not disgust. Sometimes I think, oh, brilliant, that minus 1 makes everything so much easier. And then the next day I look at it and think, God, if that minus 1, I see that again, I'm going to... Anyway. So now I'm in a position, now that I've got this gamma here, I'm in a position to define this constant here. So now I can do the PDF of the Gaussian. So the probability of P equals gamma of alpha plus beta I'll change it to red so you can see it more easily. Oh, for goodness sake. It's just there as a trick, isn't it? Can I just kill that? There's the constant. This bit does the work. Okay. That constant there makes the area add up to 1. We'll find that we make occasional reference to the normalizing constant there, but it doesn't really, it's not really very common. Well, that's great. Let's see what it does. Let's see what we want from a, well, actually, let me just show you how it operates. I'll just show you how it works. I'll just fire up R, and we'll have a look at it.